Chapter 24 Electronic Systems. Hello everyone, Dennis here. This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out free lessons from me. In this lecture, we are going to learn 5 important topics, which are how NPN bipolar junction transistors work in switching circuits, followed by various types of logic gates, which are AND gates, OR gates, NOT gates, NAND gates, NOR gates, and their truth tables. We also learn how to analyze logic circuits. Then we learn 2 important digital circuits, which are Bistable Circuits and Astable Circuits. Transistors. What are transistors? A transistor is a semiconductor device used to amplify or switch electronic signals and electrical power. There are 2 main types of transistors, which are bipolar junction transistors BJT and field effect transistors FET. What are bipolar junction transistors BJT? BJT are transistors in which require a biasing input current at their control leads. They require both positive or holes and negative or electrons carriers to operate. There are 2 types of BJT, which are NPN BJT and NP BJT. In our syllabus, we cover only NPN BJT. And here are the structure and symbol of NPN BJT. In an NPN BJT, it consists of 3 substrates. The N, which is negative substrate, P, which is positive substrate, and another N, which is negative substrate, placed side by side with each other. It has also 3 terminals. The terminal at substrate P is the base or B terminal. And the terminal in the first N substrate is the collector C. The terminal at the another N substrate is emitter E. So this is the symbol for NPN BJT, where this is the base B terminal, and this is the collector C terminal, and this is the emitter E terminal. Now, let's learn how electronic switching works. Think about this question. How do we turn on and off a switch? Let's look at this diagram. This diagram is made out of a battery, a switch, and a light bulb connected in series. So in order to turn on the switch, we need to use our finger to press the switch button, and then the switch will close. Now, the current can flow from the positive terminal of the battery, pass through the switch, then light up the light bulb, and then flow back to the negative terminal of the battery. Hence, external force, which is our finger, is applied on the switch to turn it on or off. Now, how an NPN BJT acts as an electronic switch? Let's look at this diagram. So this diagram is made out of a battery, a NPN BJT, and a light bulb connected in series. This NPN BJT acts as an electronic switch. Now, when the current flows into the collector terminal, IC, the transistor blocks the current flow because this transistor is an electronic switch which is open at the moment. Now, to turn on this transistor, first a small voltage VBB is applied at the base terminal, and if the VBB is greater or equals to the forward bias voltage VBE, then a current can flow into the base terminal. So this current is IB, and when it flows into the transistor, it will turn on the transistor. Then the current flows up from the emitter, IE, will be equals to IC plus IB. After that, these two currents will split, where the IB will flow back to the negative terminal of BBB, and the IC will continue to flow, turn on the light bulb, and then flows back to the negative terminal of the battery. BJT is called current control transistor as it can be turned on when base current IB flows into it. For BJT made from silicon, VBE equals 0.7 volt. After understanding how electronic switching works, let's discuss about light-sensitive switch. A light-sensitive switch circuit consists of two components. The first component is the potential divider component, which is made up of R1, a fixed resistor, and R2, a light-dependent resistor, LDR. The second component of the circuit is the electronic switching. The EMF of the battery is labeled as Vin as it supplies electrical energy to the circuit. The voltage across the LDR, which is labeled as VLDR, it is equals to R2 over R1 plus R2 times Vin. So this is the formula of potential divider which we have discussed in the previous chapter. So from this formula, we can see that VLDR is a proportion of Vin in the potential divider circuit and changes with LDR resistance. As you can see from this formula, R1 and Vin both are constants because R1 is a fixed resistor and the Vin is the EMF of the battery. So the only parameter that change in this formula is the R2. Alright, so this R2 will change when the resistance in the LDR changes. When VLDR is large enough, it will turn on the transistor. Alright, remember, when VLDR is greater or equals to the VBE, then the current IB can flow into the switch and turn on the switch. Now, LDR has low resistance when light shines on it. Alright, so now when the resistance in LDR is low, R2 will be low, and hence VLDR is small and not enough to switch on the transistor. Alright, so for this case, the VLDR is less than the VBE, hence the current cannot flow into the transistor, and hence the transistor is not turned on. So the light bulb does not light up. On the other hand, LDR has high resistance when in darkness. So for this case, VLDR is larger and is enough to switch on the transistor, right? So when the R2 increases, the VLDR will increase as well. So when the VLDR is greater or equals to VBE, then the current can flow, the current IB can flow into the transistor and turn on the transistor. So for this case, then the light bulb will light up. This circuit turns on light bulb automatically at night and turns off light bulb at daytime. You may wonder what is the use of this resistor. This resistor prevents excessive current to flow into the transistor. Alright, so do remember the function of this resistor. Now, let's discuss how temperature-sensitive switch works. It has similar concept with light-sensitive switch. Its circuit also has two components. The first component is the potential divider, which is made up of R1, and R1 is a thermistor, and R2, which is a fixed resistor. The second component of the circuit is the electronic switching, where a battery is connected to the potential divider. The EMF of the battery is labeled as Vin. Then a relay is connected parallel with the battery. The relay is made up of an electromagnet, and a switch. The electromagnet is connected to the NPN transistor, while the switch is connected to a bell. A diode is connected parallel with the electromagnet. Now, the potential difference across the R2 we label as VR2. It is equals to R2 over R1 plus R2 times Vin. At room temperature, thermistor has a high resistance. Alright, so now let's look at this formula. As you can see, R2 and Vin, they are constants because R2 is a fixed resistor, and the Vin is the EMF of the battery. The only parameter that we change is the R1, where R1 is the resistance of the thermistor. Alright, so at room temperature, thermistor has a high resistance. So when R1 is high, VR2 will be low. So VR2 is very low and not enough to switch the transistor on. Remember, VR2, when it is less than VPE, then current will not flow into the transistor and turn on the transistor. Alright, hence the transistor is turned off and no current flows through the transistor and the bell. On the other hand, when heated, thermistor resistance decreases. Right, so what will happen when the thermistor resistance decreases? Then the VR2 increases until at the point when it is enough to switch on the transistor. Right, now look at the formula again. So the R1 when decreases, VR2 will increase, right? Because R1 is at the denominator, then VR2 will be inversely proportional to R1. Alright, so when VR2 increases and it is greater or equals to VBE, the current IB will flow into the transistor and turn on the transistor. Right, so now the transistor turns on, then the current will flow through the electromagnet and magnetize it. So when the electromagnet is magnetized, it attracts the switch and closes the switch. Right, so now the switch is closed, current will flow into the bell and the bell will ring. There are three things that you may need to pay attention on this temperature sensitive switch circuit. The first one is this fixed resistor. So the fixed resistor at terminal B is used to prevent excess current to flow into or out from the transistor and damage the transistor. The second thing that you need to pay attention is this diode. So this diode protects the transistor from currents generated by electromagnetic induction when the relay coil is switched on or off. And the third things that you need to pay attention is the transistor does not switch on the bell directly. As you can see here that the bell is not connected directly with the transistor. Alright, so what does it mean? It means that the transistor only switch on the relay, and hence the relay is the component to switch on the bell. Okay, so how this actually helps in the circuit, because we know that the current flows through the transistor is very small. It will be in milliamperes range. Okay, so for a very small amount of current, it might not be enough to make a bell rings. Okay, so that's why this circuit, the bell has to be connected separated from the transistor. Okay, and because of this, we can more powerful bell can be used as the current in the bell does not have to flow through the transistor. All right, so as I mentioned, the transistor only use very small amount of current in milliamps range. Okay, so this principle is used in automatic fire alarm system. Now let's discuss a very interesting topic, logic gates. What is a logic gate? A logic gate is a device that acts as a building block for digital circuits. They perform basic logical functions that are fundamental to digital circuits. Nowadays, many electronic devices contain many logic gates to perform all sorts of functions and operations designed in them. These building blocks are made up of electronic switches, which we can manipulate them to perform certain functions such as signal controlling, power regulating, algorithmic functions, etc. The fundamental components of these electronic switches are transistors. A microprocessor of size 10 mm times 10 mm can contain billions of transistors in it and can perform billions of operations in a split seconds. There are three basic types of logic gates, which are AND gate, OR gate, and NOT gate. Each logic gate has its own truth table, which describes the outputs of the logic gates for given inputs. In fact, a logic system, which can have many logic gates, has its truth table so that we can understand how the system works easily. Let's discuss basic logic concept. This circuit is made up of a power source, switch 1 which acts as input 1, switch 2 which acts as input 2, and a light bulb which acts as output. These components are connected in series. Here is the basic logic concept. When current flows, logic is 1. When no current flows, logic is 0. Hence, for switches which act as inputs, when open, its logic is 0 as the current cannot flow through the switches. When closed, its logic is 1 as the current can flow through the switch. While for the light bulb, which acts as the output, when turned off, its logic is 0 as there is no current flows through the light bulb. When turned on, its logic is 1 as the current flows through the light bulb. Therefore, here is the truth table of this circuit. So when the switch 1 is open, the switch 2 is open, the input 1 will be 0, input 2 will be 0, and the light bulb will be turned off as there is no current flows through the circuit. Hence, the output is 0. Next, when the switch 1 is open and the switch 2 is closed, the input 1 will be 0 and input 2 will be 1. The light bulb will still turn off as there is no current flows through the circuit. Hence, the output is 0. The third scenario is the switch 1 is closed, the switch 2 is open, which means input 1 is 1, input 2 is 0. The light bulb will still turn off as there is no current flows through the circuit. Hence, the output is 0. The last scenario will be both switch 1 and switch 2 are closed, which means that input 1 and input 2 will be 1. For this case, light bulb will turn on because the current can flow through in the circuit. Hence, the output is 1. Looking at this table, this is actually the truth table of AND gate. We'll talk about AND gate in the next page. AND gate. So here is the actual circuit of an AND gate. An AND gate consists of two transistors connected in series. So the collector terminal of the first transistor is connected to the power supply VCC. And this is the input A, this is the input B, which they are connected to the base terminal for each transistor here. Again, there are two fixed resistors here, R and R. So these two resistors prevents excess current to flow into the transistor and damage the transistors here. Then this emitter is connected to a load RL, and this is the output that we measure here. Then we just write it as output here. The symbol for an AND gate looks like this, where this is terminal, this is input A, this is input B, and this is output terminal. The VCC and the ground terminals usually are not shown in the diagram. So here is the truth table of AND gates with input B, input A, and output. So if input B is 0 and input A is 0, which means that both transistors here are turned off, there is no current flow through the circuit, hence the potential difference across RL will be 0 and the output will be 0. When input B is 0, input A is 1, which means that the transistor is turned on. The current can flow through the first transistor but cannot flow through the second transistor because the second transistor is turned off. Hence, there is no current flowing into the load, and again the output will be 0. So similarly, when input B is 1, input A is 0, which means that the first transistor is turned off, the second transistor is turned on. The current cannot flow through the first transistor, hence it can't flow into the load. Therefore, the output will be 0. Now, if input B is 1 and input A is 1, which means that both transistors are turned on, then the current can flow into the first transistor and also the second transistor and eventually flow into the load here. Hence, we can measure an output here and it will be 1. Therefore, output is 1 when both input A and input B are 1 for AND gates. And we can write the output formula for an AND gate as AB. OR gate. This is the actual circuit of an OR gate. An OR gate has two NPN transistors connected in parallel, where the VCC is a power source and this is the input A, this is the input B. Both of the base for these two transistors are connected with the resistor here. Again, the function of these two resistors are to prevent excess current to flow into the two transistors and damage these two transistors. Then after that, there are emitters connected to a load here. So this is the output for this circuit. So the symbol for an OR gate looks like this, where this is input A, this is input B, and this is the output. For the VCC and the ground terminal, usually they are not shown in the circuit. Now, here's the truth table for OR gates, input B, input A, and output. So when input B and input A both are 0, which means that these two transistors are turned off, there is no current flows through the circuit, hence the output will be 0. When input B is 0 and input A is 1, which means that this terminal is turned on, but this transistor is turned on, this transistor is turned off. Then the current can flow through the first transistor and flow to the load here. Hence, we have the output 1. When input is 1, input B is 1, input A is 0, which means that this transistor is turned off, this transistor is turned on. Now the current can flow through the second transistor, then flow into the load. Hence, we have the output 1. So similarly, when both input B and input A are 1s, which means that these two transistors are turned on, the output will be 1 as well because the current flows through both transistors and then flow into the load here. Hence, we have output 1. So this is the truth table of OR gate. We can say that output will be 1 when either input A or input B or both is 1. So we can write the formula for the output as A plus B. NOT gate. So this is the actual circuit of a NOT gate. The power supply VCC is connected to the collector terminal of the transistor through a fixed resistor. For NOT gate, there is only one input, input A, which is connected to the base terminal through a fixed resistor R. For the emitter terminal, it is connected directly to the ground. And at this point, this is where the output is measured. So this is the symbol for a NOT gate, which looks like this, where this is the input A and output. So here's the truth table of a NOT gate. For input A, when it is 0, which means that this transistor is turned off. So what will happen is the current will flow through this resistor and flow into the output here. Right? So when there is a current flowing at this point, then the output will be 1. So when input A is 1, which means that this transistor is turned on, then the current will flow through the transistor directly to the ground. Alright, then the output will have no current flow through it. It is something like a short circuit from this point to this point. Okay, hence the output will be 0. So from here you can see that when input A is 0, output will be 1. When input is 1, output will be 0. So output is 1 when input is 0. NOT gate inverts the input. So we can write the output as A bar. Sometimes it is called inverter. After understanding how AND gate, OR gate, and NOT gate works, let's learn how to analyze simple logic circuits. Here is an example. Develop the truth table of the following circuit. And here is the circuit with two inputs, input A and input B, and one output, output Z. At this point, point C, it is the output of the AND gate, and C equals to AB. At point D, it is the output of the OR gate, and it is equals to A plus B. At point E, it is the output of the NOT gate, and it is equals to C bar. For output Z, it is the output for the AND gate, and it is equals to DE. Now, let's build the truth table of these circuits. So, there are 4 possible combinations of inputs A and B, which are 0, 0, 0, 1, 1, 0, and 1, 1. At point C, which is the output of the AND gate here, AB. So C will only be 1 when both AB are 1s. The rest will be 0. Hence, the result for C will be 0, 0, 0, 1. For D, it is the result of the OR gates, and it will be 1 when either A or B is 1 or both are 1s. Hence, the result for D will be 0, 1, 1, 1. For E, it is the inverted C. Hence, the output of E will be 1, 1, 1, 0. And lastly, the output Z, it will be the AND result of DE. Hence, the result of Z will be 0, 1, 1, 0. So this is the truth table of this circuit. Next, we want to learn 2 special gates. The first one is the NAND gate. So NAND gate is actually combination of NOT and AND gates. It inverts AND logic outputs. Here is the symbol for NAND gates. with an AND gate with a circle in front with input A, input B, and an output. So the circle or the bubble means not. So here's the truth table for NAND gate since it inverts the AND logic output. So when input B, A both are 0, it will be 1. When B, A is 0, 1, the output is still 1. 1, 0, it will be still 1. 0, 0, 1, 1, it will be 0. Output is 1 when both input A and input B are 0. Hence, output equals to AB bar. The next special gate that we want to learn is NOR gate. The NOR gate name comes from NOT and OR gates. It inverts OR logic outputs, and this is the symbol of NOR gate, with an OR gate and a bubble in front of the OR gates. Two inputs, input A and input B, and one output here. So here's the truth table since it inverts the OR logic output. So when input B and input A both 0, the output will be 1. 0, 1, the output will be 0. 1, 0, the output will be 0. 1, 1, the output will be 0 as well. The output will only be 1 when neither input A nor input B is 1. Hence, the output equals to A plus B bar. After understanding how NAND and NOR gates work, let's analyze simple logic circuits. Here's an example. Develop the truth table of the following circuit. Here's a circuit with two inputs, input A and input B, and one output Z. This output C is the output of the NAND gate. It is equals to AB bar. At point D, this is an output of the NOR gate. It is equals to A plus B bar. At point E, this is the output of the NOT gate, which is equals to C bar. For the output Z, it is equals to DE bar. So let's build the truth table. So for the AB, again, there are four possible combinations 0, 0, 0, 1, 1, 0, and 1, 1. For point C, it is AB bar, hence the result will be 1, 1, 1, 0. For point D, it is A plus B bar, so the result will be 1, 1, 0, 0, 1, 0, 0. For E, it is C bar, hence the result will be 0, 0, 0, 1. For Z, the result will be 1, 1, 1, 1. So this means that this circuit will always produce 1. Let's analyze this circuit. So this is a NAND gate where both the inputs are tied together into one input A. So again, this is AA and this is the output. So the output will be AA bar. So the truth table for this circuit will be for A, when it is 0, the output will be 1. When A is 1, the output will be 0. As you can see here, this is the truth table of NOT gates. In other words, this circuit is an equivalent circuit of NOT gates. Right, so now let's analyze another circuit here with input A, input B, and output. At this point, this is point C, and the second NAND gate is also, the inputs are tied together to C. So this will be input C and C. So here's the truth table. Okay, for AB, there are four possible combinations 0, 0, 0, 1, 1, 0, and 1, 1. So
the output C will be 1, 1, 1, 0. Then for the output for this circuit, it will be 0, 0, 0, 1, since the second NAND is the equivalent circuit of the NOT gates. So compare the input and the output results. We can see that this is the truth table of AND gates, which means this circuit is equivalent circuit of AND gates. Let's analyze another example here. Develop the truth table of the following circuits. So here is the circuits with input A, and this is also A, input B, B, and output Z. So at point C, this will be, and point D here. So point C will be AA bar, point D will be B bar. And the output Z will be CD bar. Now let's build the truth table. We have AB with 4 possible combinations 0, 0, 0, 1, 1, 0, and 1, 1. For output C, the result will be the inverse of A, and which is A bar, which is 1, 1, 1, 0, 0. For D, it is BB bar or inverse of B, hence the result will be 1, 0, 1, 0. For the output Z, it will be CD bar, hence the result is 0, 1, 1, 1. Now compare the uh, logic for AB and Z. It is actually the truth table of OR gates. Hence, this circuit is equivalent circuit of OR gates. Now, let's discuss the bistable circuits. Think about the situation of an anti-theft car system. After activating the anti-theft system, the car remains silent until an intruder accidentally triggers the alarm system, which means set button is pressed by unauthorized opening the car door. The intruder tries to turn off the alarm system by closing the car door again. But this does not work. The car alarm system continues to ring even though the car door is repeatedly opened and closed. The alarm system can only be turned off when the reset button is pressed by the car owner. This can be done with a bistable circuit. A bistable circuit is a circuit where the circuit is stable in one of two states and will not change its state until the other switch is pressed. SR latch is a very important component in bistable circuit and astable circuits. Now let's learn how SR latch works. An SR latch consists of two NAND gates. The first input for the first NAND gate is labeled as S, which stands for set. The first input for the second NAND gate is labeled as R, which stands for reset. The output for the first NAND gate is connected to the first input for the second NAND gate, and the output for the second NAND gate is connected to the second input for the first NAND gate. The output for the first NAND gate is labeled as Q, and the output for the second NAND gate is labeled as Q bar. So Q bar is designed so that it is always opposite with Q. Now let's look at the NAND gate truth table. So from this table, we can see that any one input equals to 0 will give us an output equals to 1. So there are three cases that we can study from this SR latch. Case number 1. When S equals to 0 and R equals to 1, the Q will be equals to 1 since the S equals to 0. Remember from the NAND gate truth table, as long as one of the inputs is 0, we'll get an output of 1. Hence, when S equals to 0, when here is 0, the Q will be 1. For the Q bar, it will be equals to 0 as Q bar is always opposite with Q. Okay, now let's label for the circuit when this 1, here will be 1. So when this 0, this will be 0. Okay, now we'll move on to the next stage when S is 1, R is 1. So when this is 1, R is 1, the Q will be equals to 1. Alright, so this is an AND gate, 1, 0, this will give us 1. So the Q bar will be 0 because 1, 1 will give us 0, and also Q bar is always opposite with the Q. Alright, so this stage is called memory state because the outputs remain the same even though the input has changed. Let's look at case number 2. When S equals to 1, R equals to 0. Okay, when R equals to 0, which means Q bar will be equals to 1. Okay, then Q will be equals to 0 because both will be always opposite with each other. Right? Now let's update the circuit here. The Q is 0 and Q bar is 1. Right? So which means this is 0, this is 1. Okay, so now when the input has changed, S is equal to 1, R equals to 1. So this is 1, this is 1. So what will happen to Q? Q will be equals to 0 because both inputs are 1s. So this is 0. And for the Q bar, it will be 1 because 0, 1 will give us 1, or it is always opposite with the Q. So again, you can see that this will be the memory state because the output remains the same even though the input has changed. Let's see case number 3. So when in case number 3, both S and R are equals to 0. So based on the NAND gate truth table, Q1 will be 1, Q bar will be equals to 1 as well. Alright, but when we want to design SR latch, we want the Q bar is always opposite with the Q. Hence, this is an invalid state. To summarize all the 3 cases, here is the truth table of this SR latch. So for the SR, we have these 4 possible combinations 0, 0, 0, 1, 1, 0, and 1, 1. Okay, from case 3, we know that when both SR are 0, 0, it will give us an invalid function because the results are undesirable. When SR both are 1s, it will be in memory states where the output will remain the same. When the S is 0, R is 1, the Q will be 1, Q bar will be 0. On the other hand, when S is 1, R is 0, the Q is 0, and Q bar will be 1. Alright, now let's look at this column. To set Q to be 1, the S must be 0 and the R must be 1. So 0, 1 gives us 1, 0. This is the set function. Now, this row tells us to set Q to be 0, R equals to 0, and S must be equals to 1. So this is the reset function. Okay, because we want the output to be 0. And from here, SR latch is an active low component because the input S has to be 0 so that we have the desired output here. Right? You can see that when S equal to 0, it is a set function, the Q become 1. So when you want to reset it, right, the reset button have to be 0 so that the output will be 0. Hence, it is an active low component. Now, let's go to this simple car alarm system. Here is the circuit. We have the SR latch, and we have the set and reset button. Both are connected to the ground. Okay, when S and R are not pressed, the logic is 1. When S and R are pressed, the logic is 0. As you can see from the circuit, when this switch is closed, it will go to the ground, which means logic is 0. When it is open, then the logic is 1. Okay, so the output is connected to a siren. Now here's the truth table for this simple car alarm system. So now at first it is in initial state, which is in memory. Let's assume it to output is 0, then the siren is not triggered. So SR must both be 1 1 because both are not pressed. Now remember the case where theft, the thief or the intruder tries to open the car. When the intruder opens the car, it actually presses the S button. Then S is 0, the R is 1. So this sets the Q to be 1 and hence current flow into the siren is triggered. Then the intruder tries to turn off the alarm system by closing the door, which means that the set is not pressed and it will be 1. The R is still remain as 1, but it is in memory state. The Q will still remain as 1. Hence the siren will continue to ring. So now the car owner press the reset button where the R becomes 0, the S will be 1. Hence the output will be 0. So siren is turned off. So after releasing the reset button, the Q will still be 0 because it is in memory states where there is no sound for the sirens. So this is how a simple car alarm system works. Simple fire alarm system works very similarly with the car alarm system. And here's a circuit. It has the SR latch, where the R is the reset button, while the S is connected to a potential divider with a thermistor in as the R2. So S will remain 1 until resistance in the thermistor drops when the temperature is high. On the other hand, when R is pressed, the logic is 0, or else it will be 1. The output Q is connected to a siren. So here is the truth table for this simple fire alarm system. Initially, it is in memory state, which means that the output is 0, the siren is off, and both SR are 1. So when fire is detected, the temperature is high, the resistance in the thermistor is low. Hence, the S will be 0, the R will be 1 as it is not pressed, the Q will be 1. The siren is triggered. So when the temperature goes back to normal, the resistance is high, which means that S is 1, R is 1. But the Q will still remain as 1. The siren will continue to ring. It will continue to ring until R is pressed, where the S is 1, the R is 0, the Q will become 0, and the siren is turned off. When R is released, the S is 1, the R is 1, the Q will still remain as 0 as it is in memory state, and there is no sound. Here, this is how simple fire alarm system works. Lastly, we discuss astable multivibrator. What is an astable multivibrator? An astable multivibrator is a type of free-running oscillator where it does not have permanent meta or steady state. It continuously changes from one state low to the other state high and then back again to its original state. This continuous switching action from high to low and low to high produces a continuous square wave output. And this is how it looks like. The time measured from this point to this point is the period t. The time constant or the period for a NAND gate astable multivibrator is given by the formula t equals to 2.2 Rc in the unit of seconds S, where the R is the resistance of resistor used in the circuit in ohms and the C is the capacitance of capacitor used in the circuit in farad F. To calculate the frequency of the square wave, it is just F equals to 1 over T in the unit of Hertz, Hz. Let's learn how NAND gate Astable circuit works. A NAND gate Astable circuit consists of two NAND gates, where these NAND gates are equivalent circuit of a NOT gate. So the output for the first NAND gate is connected to a capacitor and to the input of the NAND gate number 2. So the NAND gate number 2 output is connected to the inputs of NAND gate 1. A resistor is connected parallel with NAND gate 2. So this is input 1, this is input 2, this is output 1, and this is output 2. So let's build the truth table of this circuit. When initial states, the input 1 is 1. So, which means that output 1 is 0 because this is equivalent circuit of NOT gate. And output 2 will be 1 since output 2 will be always opposite of output 1. And this will be input 2 will be 0 because again this is the equivalent circuit of a NOT gate. If this 1, this must be 0. Okay, and the current will flow from this point through the resistor and charge the capacitor. Okay, because as you can see here, the potential difference O2 to I2, right? This is higher than this point, then the current will flow through here and charge the capacitor. So capital C is charged through the R. When capacitor C is high enough to discharge, then input 2 will be 1. Hence, output 2 will be 0. And input 1 will be 0. And output 1 will be 1. So, the current will flow through output 1 and discharge capacitor C through the resistor R. So, the capacitor C is discharged through R. After discharging some time, the capacitor C is low and ready to charge again. Hence, the input 2 will be 0 and the output 2 will be 1, which means that input 1 will be 1 and output 1 will be 0. So look at the result for this state 1001. It repeats with the first stage 1001 here. So initial state is repeated. And the result for the next state will be 0110 and 1001 and continue. So look at output 1 here. It produces a continuous square wave output, which will look like this: 0, 1, 0, 1, 0, 1, and this wave continue to repeat. This is how NAND gate Astable circuit works.
Alright, that's all for this video. Thanks for watching and I hope you enjoy it. Do you have any question or doubts to ask? Feel free to write it down in the comment area. I would love to hear from you. Do you like this video? Please don't forget to like it and share it with your friends. Alternatively, you can also enroll this full revision course at Udemy. At Udemy, you can track your learning more effectively. Download my notes in printable PDF form,
take a summative quiz at the end of each chapter. Get your first-hand updated contents from me. Get quicker response from me, and many more. You can get all these benefits at a very affordable price. It is one-time payment, no recurring fees, no hidden costs. This saves you thousands of dollars on expensive tuition fees and revision crash courses. And most importantly, your precious time. Finally, you can do your revision anytime you like, anywhere you prefer. All is available within your fingertips. Check out the description below this video and click on the enrollment link to register the course at discounted price. Alright, until then, see you in the next video. Have a great day ahead.